So these slides, Data Communication 101 and 102, the material is contained mostly within Chapter 1 of our text. Okay, some is in Chapter 2, but most of this is from Chapter 1. We had talked a bit about the scope of the reading. You know, there's just so much stuff I'm throwing at you. So in the text, make sure to read Chapter 1 and then Section 1 of Chapter 2. Okay, that's sufficient for our exam. Okay.
When you said the text, you meant
The corrosive.
corrosive.
Yeah. Yeah. And then in the Donahue, actually let me trying to be super organized here and track what is going to be on exam 1. So I do this review page. Hopefully it's there. Yeah. And actually, I think this is almost more for my help than for yours, but this is basically keeping track of what we talked about week by week, with probably the most important part, identifying what is covered on exam 1, and okay, so text chapters 1 and 2, I need to change that. All of chapter 2 is not required, just section 1, chapter 2. But in Donahue, chapters 1, 2, 3, 4, and then 5.1 and 6.2. And then this represents the set of code that we're looking at in the exercises and the homework. And that's it. So that's, at this point, it's still for exam 1. We're honing in on all the material that's going to be covered by exam 1. Yes?
Did you say 5.1 and 6.2 for
Yes.
Donahue?
Correct. All right. That is a very noisy class.
I was just going to say that.
It cannot be an engineering class. We're quiet. All right. So, basically we talked about at the physical layer how computers communicate, and it's all about translating ones and zeros into changes in energy in one form or another, and that energy propagates over any physical medium. So now, physical medium, there's this concept called channel bandwidth. Okay, and so any physical medium has a maximum bandwidth associated with it. So that means that there is a maximum data rate at which you could possibly hope to use that physical medium for maximum speed in terms of sending data over. And the speed, again, goes back to physics. So the bandwidth is actually defined in terms of frequency. Okay, so a Ethernet or coax cable, the bandwidth frequency is from 0 hertz to about 2 gigahertz. Okay, and for wireless, the bandwidth is
if you can sort of picture in your mind, that at 0 hertz, going up to 700 for 50 megahertz. That's like FM, AM, FM radio. Then we get into TV, and then when we get over a gigahertz, we start getting into, well, anywhere from 600 to, starting at 600 megahertz, we start getting wireless data is using bands. So with that spectrum, basically the FCC, so the government, has divvied up the spectrum into bands, and they tell who is allowed to use the specific bands. So Wi-Fi has multiple sort of chunks of spectrum: 2.4 gigahertz, 5 gigahertz. Cellular operators have chunks sort of spread from the 600 megahertz range all the way up to, well, now up to 60 gigahertz. It's very well managed by the FCC, but so when I say channel bandwidth, that means the channel that represents the portion of the spectrum that's being used on that physical medium. With Ethernet, or like cable with coax, all of the spectrum is going to be used. Okay, and so that's why we're able to get, or we're able to see in excess of 100 gigabits per second on Ethernet, because the bandwidth is large, 2 gigahertz. In fact, the formula for telling the maximum rate is given by what's known as the Nyquist theorem. So B is the bandwidth, whether it's 2 gigahertz or like in the world of cable. Okay, so we have a coax that comes to our house, and there's a modem. Even though the cable spectrum is 2 gigahertz, it is carved up into almost 200 different channels that are roughly 6 megahertz large. So B in the formula is the bandwidth. The example I'm going to use here is so a TV channel, and this is true over the air or over a coax cable, uses a 6 megahertz channel. So B is going to be 6 megahertz. K is the number of, it's basically the amount of data that is encoded in each energy switch, energy transition. Okay, and so we'll say in the example, if K is 4, log base 2K would be 2. So the maximum data rate over this channel would be 6, so 24 megabits per second. Now,
D is measured in megabits per second then, not megahertz?
At this point, we can assume it's megabits per second, right? Yeah, there's sort of a fine blurry line between talking about bandwidth and frequency and in bits per second, but this is the data rate in bits per second. There's another formula, so if we were taking an ECE class, okay, there's basically a whole class that is talking about information theory, right? That's sort of behind the physics of this. But there's another formula, the Shannon's formula, which basically then it's based on this. This assumes unrealistically an ideal channel, meaning no noise. Okay, Shannon, it predicts the max data rate for a given channel of a certain size, taking into account a parameter that represents the noise level on the channel. So it's a much more accurate estimation of the maximum data rate. Yes.
Over there.
There was a
Oh,
question up there.
Yeah.
So how many signal levels would be in a channel like an Ethernet or something?
Okay, so that's a good question. So with Ethernet, so it could be like 64 QAM, 256 QAM. So this, my example with 4 is very, very small, right? So these days it's approaching like over 1,000 bits of data can be encoded within very complex frequency manipulations that the fundamental limit is over that rate. There's a finite rate at which the energy can flip from one, basically a positive to a negative. But there's almost an infinite combination in between. And that's where all the data can be sort of inserted. Data count 1 to 2. So some of this, you know, some of this I've talked about, some of this you picked up from the reading. We are talking about what's called packet-switched networks. And so data is divided into small blocks called packets. And so there's the issue of how do you fairly share the resources of that network across competing users. And the networking protocols that are at play, it's a part of the design as to how fairness is handled. Okay, so I think I've drawn a picture or two that shows a sender and a receiver and an arrow representing a packet or a message being transmitted. This is a bit more detail here. So at the host, we'll say this is T0, and then we'll say this is T1. T0 represents the time when the very first bit of the frame hits the physical medium, and it takes a while for the transmitter to send all the data. And so T1 represents the time at which the very last bit of that frame is sent. Okay, so that's basically the transmission time. And at the receiving end, let's call this T0 prime. and this T1 prime. So T1 prime minus T0 prime should be identical to T1 minus T0. If we say, call this the time at which the host A, it's T0 time, and this is T0 prime. T0 prime minus T0 represents what?
Time it takes to send the packet from the host to the receiver.
Exactly. So it's the time it takes for the bits, so that energy, to propagate across the physical medium.
Okay, and
The upper bound for
that speed is the speed of light.
okay, but depending on the physical medium, it may slow it down, so it may not propagate at the speed of light. But anyways, the propagation time is actually quite significant. So between the time it takes electromagnetic energy to travel from the East Coast to the West Coast is about 30 milliseconds. Okay, from here to Asia, over 100 milliseconds. Okay, I'm considering diverging here. Okay, so you all are familiar with SpaceX? Okay, so the thing that they're launching right now is a basically a number, well, a large number, like 24,000 satellites that will provide coverage across the globe, and they're at a fairly low orbit. Okay, and so the one form of connecting two computers is via a satellite hop. Okay, and that's been around for 50 plus years. So typically, satellites, are I don't know how many miles out in orbit, but the round trip time from Earth to the satellite could be on the order of a second. So what SpaceX idea is to create this, basically a mesh, okay, that's lower. So the round trip time is on the order of hundreds of milliseconds, which is roughly an order of magnitude lower than typical satellites. But their network will provide internet access in every single location on the Earth. Okay, and so Musk, right, the owner, used to be the owner, he has a vision of whatever he does helps people. So this will help people. It will provide internet access to remote, desolate places in the world. And the reason is it avoids the huge round trip times associated with typical satellites, and reduces it to something that's more usable. Yeah.
Do you know how much slower they are compared to like physical mediums like here on Earth versus it going into a satellite?
Well, the limit is still the speed of light,
Okay.
but it's always the distance. So the distance to a DoD satellite that's been flying up there for 30 years is huge, like on the order of, you know, distance-wise, potentially around the world. Okay, and in fact, SpaceX round trip time is actually going to be lower than, for example, a fiber optic cable from North America to Europe. So, you know, imagine that distance and the time it takes for data to propagate through a fiber. That is greater now than the time it takes to go to have a link between a SpaceX satellite and you know, with two end stations, one in North America and one in Europe. Yeah, it's cool. Okay, end of my divergence. So we talked about things can happen when data is in flight, right? Bits might become inverted, dampened. The noise level could make it difficult for the receiver to reliably decode those energy transitions to pull out the ones and zeros. Those are called bit errors. There's, in any transmission, there always will be some error checking that occurs. So at the receiver, it's going to receive the data, and then it will perform most likely a CRC, which basically is a checksum. And it's an algorithm that will be performed on the data that was just received, and it'll compare the number produced by the algorithm with the CRC number that is attached to the end of the frame. And if they're the same, then we're 99.99999% positive that the frame, that none of the bits have been changed from the sender to the receiver. Yes?
So the CRC number, what layer of the network stack is that checking?
Okay, so that's a great question. So CRC, it's think at the framing layer. So in fact, that's a good segue to this. Okay, so this is a picture of a frame. Okay, and it's actually an Ethernet frame, but the Ethernet frame format is widely used with other physical mediums, like Wi-Fi uses this same frame format. The cable networks use the same frame format. So this is a frame. It's produced by the link layer and supplemented by the physical layer. So again, sort of imagine the stack at a sending host. There's the application, the transport layer, it hits the network layer, that would be IP for us in this class. Coming out of the IP layer is an IP datagram, okay, which we'll look at in excruciating detail later. That then goes down to the link, where there could be multiple interfaces on that machine. So part of the network layer is to figure out which IF, which interface to use. Once it figures that out, it builds the frame and passes that to the link layer. And so from here to here is referred to as the MAC header. The IP datagram goes in the payload, and there's 4 octets for CRC. So it's the link layer. Once it computes, or once it has assembled the frame, it computes the CRC, runs the algorithm on all the data, and inserts those 4 octets here. That then goes down to the physical layer, and there's some octets at the very front end of the frame where it is physical medium specific as to exactly what that looks like. So it'll look different in Ethernet. Those bytes will look different from Wi-Fi. Okay, so it's basically data that allows the transmitter and the receiver to sync up. Once they sync up, then the receiver should be able to receive the rest of the frame. The most important parts of the MAC header for us are, so when it leaves the sending host, it'll have the source that hosts it, the source MAC address. Okay, so every network card, whether it's an Ethernet or a Wi-Fi adapter, will have sort of burnt into it a MAC address, 6 octets long. So the source MAC, the destination MAC. So that means the sender needs to know the receiver's MAC address. Okay, and we'll talk about how that is done. There's a dynamic protocol called ARP, which is used, that allows the sender to learn the destination's MAC address. And again, these are not IP addresses. These are machine addresses. The 2 octets for the total length, total number of bytes in the frame. This is more or less used by the link layer to figure out how to forward upwards the data in this frame. So in other words, the link layer is being multiplexed by other protocols. So for example, there might be a LAN protocol, like there's something way back when called NetBIOS. There's other examples of different networking protocols that are different than TCP/IP. The code specifies the type of networking protocol. So if this is an IP datagram, the code would indicate it's an IP payload. Okay. So the last thing I'm going to say about this slide here, or this set of slides, talk about how errors can happen. Error detection, we talked about CRC algorithms and how that can perform a error detection process. So if the CRC fails, the frame is just discarded, thrown away. But what if the endpoints need to know that the frame was discarded? Right? In other words, what if the nature of the application that's running needs a reliable link? Okay, so in that case, there's a couple of options. Certain MAC layers will actually provide their own recovery. So for example, Wi-Fi, whenever it transmits a frame in normal operation, the receiver should send an app. And if the app doesn't arrive within a certain amount of time, the sender, again, this is going on at the link level, will retransmit. Okay? Over Ethernet, that does not happen. Because an Ethernet is typically a much more reliable medium than wireless. At the transport layer, that's where an application will decide if it wants reliable or unreliable network connectivity. For unreliable, it will choose UDP. For reliable, it will choose TCP. Okay, so we're starting out with our examples looking at UDP because it's much simpler. It's, as we'll see when we step through the code, the application just does a send, and that data just gets stuffed into an IP datagram and gets sent out. And at the other end, the receiver will do a receive from on the socket, and when that datagram arrives, it unblocks and it magically has the data. If the packet is dropped, then this gets back to the discussion we had the other day about setting a timeout, right, at the send side. So an application that uses UDP, if it needs reliability, it would have to add it in the application. With TCP, it's very different. So the code actually looks similar, but the application just, if it has data to send, it just stuffs it into the socket. It could do multiple sends, and all that data basically gets queued, and the TCP stack at that sending side will interact with the TCP stack at the destination to determine how all that data will be sent. Okay, and a part of that determination is if the receiver sees a packet is dropped, it'll send back an app and say, sender at the TCP layer, you need to retransmit packets X, Y, and Z. Okay, and so all of that goes on underneath. The application has no knowledge of what's happening. Okay. Errors can be due to physical medium impairments. Yes.
At each hop
Yeah.
between the source and destination, is each hop going to check the CRC to make sure the frame is correct, or is it just going to check the MAC addresses and say forward on to the next person?
Okay, that's a really good question. The TCP/IP was developed back in the 70s when the nature of networking was assumed to be unreliable. So they went overkill in terms of having error detection pretty much at every single layer. Okay, so the answer to your question is yes. At each hop, the CRC is performed, and further at each hop, when we start looking at the IP header, we'll see that it also has an equivalent to a CRC, and that check is done at each hop as well. So it's sort of like, you know, being done multiple times per hop. And but it's still possible they have shown that it's still possible for erroneous packets to make its way to the endpoint correctly. And it's either due to software bugs, or there is a very, very tiny probability that a CRC algorithm will miss an error.
Does it change it if it detects it and continue it and send the corrected code to the next hop?
So if it, like if a router, if it detects an error,
Yes.
it'll drop it, and usually that's all that'll happen. So it won't try to correct it or do anything else. There's other types of errors where the IP layer might get a packet and not know what to do with it. And there's a protocol in TCP/IP called ICMP, the Internet Measurement and Control Protocol. The router would issue a error message back to the sending host. But at the link layer, it doesn't do that. So really good question. So link layer, just think computer to computer. It's one link at a time. And so the recovery is just between those two entities. While at the network layer and transport layer, it doesn't have to be between just two connected machines. It could be between hosts or routers or anywhere, communicating an error back to a offending host. Okay, another way that errors can occur, not necessarily errors, but it's if the network becomes congested. Okay, so imagine a sender that's sending very, very fast, and imagine a receiver that's receiving or doing reads off the socket at a slower rate. So that data has to go somewhere. It's going to be put in buffers, and there's quite a large number of buffers over the path. So every single output interface, so every single Ethernet card or Wi-Fi adapter has a buffer, a device buffer. Every socket has a send buffer. Every router has effectively a forwarding buffer. But in the simplest case, just imagine a sender, a receiver,